Problem number 80. Lactic acid gives sour milk its distinctive taste. Lactic acid is also an ingredient in several skincare products that purportedly smooth fine lines and improve skin texture. So here's a template for the molecule. The Lewis structure isn't done yet. We got some lone pairs to add. So here's what we're supposed to do. With that starting structure, first add lone pairs where needed, and then count the total number of valence electrons in lactic acid. Okay, so add the lone pairs where needed. Now, looking at this, the hydrogens and the carbons are all good, because hydrogens all have one bond, and carbons all have 4 bonds. You can look at any carbon and count all 4 of its bonds. So this one, 1, 2, 3, 4. All of the carbons and hydrogens are good. It's the oxygens that you need to look out for. Oxygens, remember, have 6 valence electrons. 1, 2, 3, 4, 5, 6. So there's 2 unpaired ones, and oxygen likes to form 2 bonds. So this one has 2, this one has 2, and this one has a double, which is 2. But each of they're all missing their 2 lone pairs. So let's add the lone pairs. There's that one. 2 lone pairs on this one, and 2 lone pairs on that one. So that's the first part of A. And the second part, count the total number of valence electrons in lactic acid. So this is kind of like a big counting. So basically, all of the valence electrons are represented in the Lewis structure when it's finished. So each bond is 2. So 2, 4, 6, 8, 10, 12, the lone pairs as well, 14, 16, and don't forget this one, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Hope I did that right. So 36 valence electrons, and hopefully you were following me counting and I didn't miss anything. Okay, B. Determine the shape around the 4 indicated atoms. So you got these 4 atoms, and to do this, we're going to need the next table, which helps us do molecular shapes. And let's find that. Here it is. Table 4.2. Okay, the way you determine the shape is you count the number of atoms that one is connected to, as well as the number of lone pairs, and then this will tell you the shape. So atoms and lone pairs, and you get the shape. So looking at the this carbon right here, okay, going over here, I count 1, 2, 3, 4 atoms, 0 lone pairs, looking for 4, 0. Okay, 4, 0. So that's a tetrahedral carbon. So this one right here is tetrahedral. I'll just say tetra. And then what's the next one? This oxygen right here. This oxygen has 2 atoms it's connected to, and then 1, 2 lone pairs. So we're looking for 2, 2. That's down here. 2 atoms, 2 lone pairs. That's bent. So we'll say that one is bent. And then this carbon right here, I count 1, 2, 3 atoms, 0 lone pairs. So 3, 0. That's trigonal planar. Trigonal planar. And then the last one is this oxygen right here. That is just like that oxygen, 2 atoms, 2 lone pairs. So 2 atoms, 2 lone pairs. That one is bent as well. So it's hard to perhaps imagine what the overall shape of this molecule looks like, but I got a picture of this somewhere. Let me show you the picture. Here it is. Here it is. If you could imagine this this molecule is kind of rotated a little bit. Okay, so you got the carbon on the left. You got this carbon on the left. Is the atoms around it are tetrahedrally arranged. So it's kind of hard to see that. One's coming behind the carbon, and then these two are kind of, these three, I'm sorry, this hydrogen, and this carbon are kind of being pushed out towards you like an umbrella. And this carbon is also a tetrahedral. We weren't asked for that shape, but this oxygen is bent. The atoms around it are bent. This one is trigonal planar, like a flat triangle, and then this oxygen is bent. So here, this has been kind of flipped around. The carbon double bond in the structure is actually pointing up, whereas the bent oxygen is pointing down. So if you can imagine this little single bond kind of spinning around, so these two groups would flip places. Single bonds can rotate. So this molecule, you know, it's a flexible molecule, and it does change its shape overall. But you can look at any one atom and say, okay, well, this is trigonal planar, this one is bent, this is tetrahedral, this is bent, and that's tetrahedral. Here's the skeletal structure, which represents the molecule. Well, the last part is actually part C. So we finished part B. Part C is label all the polar bonds. Well, the carbon carbon bonds are nonpolar. The carbon hydrogen bonds are nonpolar. The only ones that you got to watch out for are where the oxygens are. Oxygen has an electronegativity of, let's see, the electronegativity of oxygen is 3.5. Okay, and carbon is 2.5. So that's a pretty large difference. That's a difference of 1. So the oxygens are pulling electrons away from the carbon, and so here I can draw, you know, a bond dipole right here. Where's another carbon oxygen? So the oxygen's pulling these away from the carbon, a bond dipole right there. This one's pulling the electrons away from the oxygen. Any more oxygen carbon bonds? I don't say. Okay, we got oxygen hydrogen bonds here and here. So 3.5 versus 2.1. That's a difference of 1.4, which is being pulled towards the oxygen. So here, the oxygen's pulling it away from the hydrogen, and this oxygen's pulling it away from the hydrogen. Lots of bond dipoles here. I don't see any other types of bonds in here except for carbon hydrogen and carbon carbon. Okay, so we've labeled all the polar bonds. Is the molecule polar overall? And it's definitely polar overall. You know, you might think that this arrow cancels that arrow, and then this arrow cancels that arrow. But don't forget, oxygen, the shape of this is bent. So it might look like they're canceling each other, but it's actually bent. This hydrogen might be bending up in that direction, and so they don't cancel, and neither do these. And this one doesn't have anybody to cancel it. So I can't tell you, you know, how the arrows all add up, but you know, definitely the oxygens are sucking electrons wherever they are. So when you got a complicated molecule like this, it's best to not say, well, the overall arrow is pointing in such and such direction, but it's more appropriate to kind of say, well, this oxygen is pulling electrons towards its part of the molecule. This one's pulling electrons. This one's pulling electrons, and so you have some certain electrostatic character that it kind of changes to, because the molecule is flexible. All of these single bonds rotate, so the molecule changes shape overall. but it's definitely always polar in some respect. So I'll say polar